So the quantum Zeno effect refers to the fact that it's possible to prevent change to a quantum system by repeatedly measuring it in quick succession. We could say this observation confirms that a watched quantum pot never boils. Certain systems seem to need privacy to change their state, and they stay static if they're continuously observed. This minimum of privacy necessary for change to take place meets the formal definition of energy, although it's not a form we typically think of energy taking. And this text will refer to the energy required to overcome the quantum Zeno effect as transition energy. And while it will be relevant to some of the time-adjacent topics later texts touch on, it's not immediately obvious to our intuition how not being observed could be a source of energy. Now, one interpretation, and I'm not sure this is a great interpretation, but it can help to reconcile some intuitions that just won't play nice otherwise, is that in order to change its state, a quantum system that begins in state 1 has to enter into a superposition with a state 2 before there's a non-zero chance of observing it in state 2. So if the system is repeatedly observed in state 1 at an interval taking less time than it would take to enter into superposition of states 1 and state 2, the odds of observing the system in state 2 tend towards 0. So this minimum time to change state is a holon. Its behavior cannot be predicted by analyzing the behavior of smaller slices of time. And a quantum system cannot change its state without going through this transition on time unbroken by observation. So when we talk about a system with a known initial and final state that requires an interstitial period for change in state to occur, that's an image that we'll be returning to multiple times in this article. And note that the time of measurement at either end of the period of change can be fixed to an arbitrarily precise degree, but the interstitial period cannot. A moment of interaction can be placed at any point in a timeline, but this interstitial period of change has a minimum length, and attempting to further subdivide it alters the behavior of the system. This is therefore a great example of what we mean by a four-dimensional holon. Another observation that changes the way we think about time from our classical assumptions is that of the quantum eraser. So the quantum eraser is a variation on the classic double-slit experiment, reference 4. In this version, a photon is split into two lower energy photons on its way to the standard double-slit wall. One photon continues as in the standard double-slit experiment. It passes through a wall and either leaves or does not leave an interference pattern on the far side of the wall. The second holon travels a farther distance to a reading apparatus. Now, because it's a photon, it doesn't really move through time the way we think of it, but to the degree it makes sense to say it, this second photon spends more time in transit. And the results of this experiment are pretty counterintuitive. The observation or non-observation of the second holon actually affects whether the first holon leaves an interference pattern or not. Now, in a classical model of time, we don't think of causes as having effects before they happen. In fact, we would say that a cause cannot have an effect before it happens axiomatically, by how we define a cause and an effect. Now, I don't know whether we want to retain this axiom or not, but we won't argue against it because this text's thesis is that we shouldn't try to cut up time to that kind of precision. Both photons have their respective interactions, and they're part of a whole, a temporal holon that cannot be further subdivided along spatial or temporal lines without losing information. So this holon doesn't just span their respective locations in space. It also spans the time between the instant they're split and the instant that the second holon is measured. So the concept of quantum erasers and quantum Zeno effect demonstrate that time isn't, as we think of it, infinitely divisible. Now, it is divisible. Interactions can be thought of as happening at precise instances, but there are also stretches of time that are more accurately described as being extant. And systems that are extant in time display certain behaviors only if they're allowed to exist on a continuum that stretches across multiple points in time. And we have to imagine the time dimension as containing not just points, but fields. So experiments like these don't mesh well with most mainstream intuitively adopted models of time. There are, however, several theories that, while they're not typically used to examine time specifically, do seem to better fit this data. And although this text is focused on better intuitive models of time, it is valuable to study these existing theories in the more narrow sense their authors presented them in, before we seek to relate them to everyday experience. Now, one of these theories is that for a theory of quantum gravity to give rise to Einstein's theory of special relativity, it's necessary to posit a general boundary to one's model rather than presupposing an infinite spacetime, reference 6. And key to this approach was the idea that for such a bounded region, as the originator puts it, transition amplitudes are associated with regions of spacetime, and states are associated with their boundaries. So we can see here the beginning of a hard data model in which definitive three-dimensional states exist only at the boundaries of four-dimensional regions of spacetime, with the four-dimensional interior being represented by a linear combination of states. Now, these boundaries were proposed to ensure that quantum physics display the same locality of results as relativity. But the concept is very similar to the temporal holon concept that this text leans on so heavily from, let's say, a more philosophical and lay approach. Another theory that's relevant is Penrose and Hameroff's orchestrated objective reduction theory, the ORC-OR theory. And that similarly posits bounded spacetime. So they attempt to address the hard problem of consciousness, and they posit that a given superposition has its own spacetime curvature. And each instance of consciousness, each experience, happens when more than one of these curvatures interact, reference 7. And similar to the theory we just mentioned, this model posits a collection of bounded regions whose internal states are quantum, but whose interactions follow a classical model. Now, another theory that approaches subjective experience is that of Tononi. And Tononi arrived at this model through studying consciousness and neural structures, reference 8. Tononi's model is actually mathematically rigorous, and it relates subjective experience inside a given boundary to both the amount of information it generates and the degree to which the information integrates. So Tononi first defines the amount of information generated as the scale at which uncertainty is reduced. And to describe what he means by uncertainty reduction, he uses the example of a dice, which has 6 possible states while tumbling, but they're reduced to 1 when it lands. So this image of uncertainty being reduced obviously relates very closely to the description by theorists like Haeckel and Penrose of a system being in superposition across a 4-dimensional continuum before it collapses into a 3-dimensional state. Now, Tononi's description of the integration of information requires more abstraction, and this one took me a while, so you might want to pause the video after I go into it. So to explain this concept, the theory in question is modeled as a network of nodes that have values at the nodes and connections between them. So the number of different values represents the total data the system can contain. The degree to which a change to one of these values changes the values of the nodes to which it's connected, and the nodes to which those nodes are connected, represents the degree to which the information is integrated. So specifically, it's the amount of change that the nodes with the fewest connections to all the others have that determines the degree of integration. So this description allows the model to determine the proper boundaries of a conscious system, because if nodes of this type are embedded in a system that can pass more information across a less sensitive link, then the experience of the larger system is indistinguishable from that of the subcomponent. Now, Tononi's research focuses on multiple subregions of the brain, but with a bit of speculation, we can also predict an embedded model of consciousness. For example, we can predict the concept of egregores from this theory. So if a group of people is able to integrate a lot of information between the members, then it meets the definition of being conscious. But the least sensitive link will typically be between team members. So it won't be the same kind of consciousness as occurs within the individual members. Within the individual team members' brains, the least sensitive connection will typically still have more bandwidth to communicate a change in state than the members can exchange between each other through practical communication. Now, if the bandwidth of the communication between members were to exceed that of the members' individual divisions, then their consciousness would no longer be functionally separate from one another. Or at least the separation would no longer be where we would intuitively draw it. If a team has major divisions in communication, for example, along ideological lines, then possibly the cleanest place to subdivide consciousness might not be at the boundaries between the team members' bodies or at the interface of their communication, but actually inside of the brain of the member who's most undecided between the ideologies driving this internal division. Now, I should mention again, Tononi's model is mathematically rigorous and deals with brain regions at the scale of neural columns and individual neurons. So he doesn't go into this kind of speculation, and I don't want him catching flack for the direction that I've taken this speculation. However, if you're inclined to think in those terms, it is a fairly small step. And it's also relevant to us here because by formalizing the meaning of individual experience, this theory can help us think more precisely about what a holon is in our context. In a philosophical sense, a holon is a fairly loose concept, and it's able to be conceptualized somewhat arbitrarily. But Tononi's work associates individual consciousness with the most information passed across the weakest internal link. And that offers the prospect of an objective boundary for an individual consciousness, which corresponds to our intuition about where a holon's proper boundaries are because of, again, the rate of information transfer and how that affects the cubist interpretation of quantum mechanics. So this quality of subjective consciousness will be important later in our exploration.